block diagram, draw the truth table. After the truth table, derive the Boolean expression, then draw the circuit using basic logic gates, right, for 16 by 1. And I think that is one of the questions in the tutorial as well, I believe. Yeah, there we go. All right. Now, the next particular thing I want to talk to you about is one of the applications of a multiplexer. One of the applications of a multiplexer, right? So I gave you the application whereby you want to select which line to go into the output. Remember we were saying, okay, you want to look at camera 3, so you do an input select and you look at camera 3. Right, so we spoke about that particular practical example. I want to give you another example, and it's over here. You can use a single multiplexer. Remember, multiplexer is just a single chip, right? Right? You can use a single multiplexer to represent sum of products. Okay, so let's have a look at this example here. Let's look at this first one over here. There's two examples, right? And if you can understand this first example, I think you should be fine. Look at this first example. Don't ignore the bottom part, all right? Okay. There we go. So somebody's given you a sum of products, or what do you call this? This is sum of max terms. I think the lowercase m is missing over here, but the fact that there's a sum, that gives it away that it's a sum of min terms, sorry. So you have a sum of min terms, right? Sum of min terms. So it says 0, 1, 2, 5. What does that mean? 0, 1, 2, 5. That means on your truth table, the outputs will occur at address 0, address 1, address 2, and address 5. Okay, so that's what we have here. But this example is a solved example. Now, how do we, in a normal situation, you would end up with a sum of products circuit. Yeah, you'll have rows of one row of AND gates, and then the last row of an OR gate. Yeah, or you would, what else would you do? You could place this into what? You can take the truth table, you can put it into what? What do you put it into? A Kano map, and from the Kano map you can extract the minimum sum of products. So that was one pathway available for you. You have the sum of products or the minimum sum of products via the Kano map, right? Now, another pathway is via the multiplexer pathway. So all you got to do is, remember your data lines, these are your data lines, these are your select lines, right? So your data lines, wherever your minimum sum of min terms address is, which is basically where your truth table is saying a 1, you just connect a 1, and all the other places you connect a 0. Right? And that is just using one chip, using one block, a circuit of how you could implement sum of min terms. Okay, right? Now, let's do another example. Something wrong here? Okay. Power. Okay, while this thing is warming up, let's continue over here. All right. Now, let's have a look at the next example, example 2. Example 2 is nothing fancy, guys, nothing fancy. Again, there are 3 inputs, A, B, and C. But in this case here, what sort of multiplexer are we using, guys? Can you tell me the name of that multiplexer in example 2? 4 by 1. Yeah, it's a 4 by 1 multiplexer. How do we know it's a 4 by 1? Well, always in a multiplexer, it'll always be a 1 if there's only one output, right? And we know it's a 4 because there's 4 inputs. Obviously, if there's 4 inputs, 2 to the power of 2 gives you 2 selectors. But the way they've configured it is they've placed a C, another input. They want to extend the range of this. They want to extend the range of this 4 by 1 input, 4 by 1 multiplexer, and have another input called C. So AB is your select line, 0, 0, 0, 1, 1, 0, 1, 1. Then you have C, two possibilities. C equals 0, C equals 1. All right? Okay. So basically you just follow the logic, right? 0, 0, which means you put two zeros here, right? C is 0, right? C, oh, okay, and this is the circuit diagram. The circuit diagram is already supplied to you. That is C, this is C bar, right? And that's fixed at 1, that's fixed at 0. So if it's 0, 0, all you got to do is you got to know, okay, if it's 0, 0, then which data line will be selected? D, 0. So D0 gets selected, so that will connect here. 0, 1, let's go to the second line. 0, 1, which data line gets selected, guys? Line number 1. So line number 1 will be C bar. Now, what is C bar? Well, there are two scenarios. You can have C as 1 or C as 0. So anyway, it says C bar over here, right? So same thing. So 1, 0, data line 2, the output F is C. If 1, 1, data line 3, that's fixed at 0. So basically, it's all just a matter of interpreting it. Now, what is the advantage? Why would we go through this? Now, if we do this homework yesterday, can you look up from yesterday's exercise when we attempted to, or was it in your homework? When we attempted to get the Boolean expression for the 8 by 1 multiplexer, right? When you looked at the 8 by 1 multiplexer, how many gates would be needed? We sort of calculated the number of gates. 7 gates. Yesterday when we looked at the Boolean expression of this thing here, yeah, I think it was part of your homework. How many gates would we need? How many AND gates would we need? 8 AND gates, and how many OR gates? 1 OR gate. So altogether 9 gates. So from what can we comment about the number of gates in order to build this multiplexer? How many gates sitting inside that? 9 altogether, right? So 9 gates would be what? 3 chips. Because if you remember, if you do 4 gates per chip, let us say there are 4 gates per chip, but really I think those 9 gates would be, each gate would be having 8 inputs, yeah? And I don't think there is an 8 input AND gate. So let us say that there is 4 gates per chip, right? Or let's say if it's a 4 input AND gate, then you can only get 2 gates per chip. So 9 gates, you'll get 1, 2, 3, 4, 5 chips. 5 chips to build this, right? Okay, if each chip was 30 cents each, right? So 5 chips, that's $1.50, right? Now, multiplexer chip, because it is a single chip, slightly more expensive chip because it's got more circuitry inside it. If you open the chip up, I mean, from metaphorically speaking, if you open the chip up, there's more gates sitting inside it, right? So it might cost $1, right? It won't cost 30 cents anymore. It will cost $1, but still $1 is cheaper than $1.50. See, so that's why we implement it. It's neater, and if you look at this, it's neater. It's not messy. Single chip does the whole job, right? So that's the advantage of this, right? And the other thing is, always remember that sometimes we can use a lower level multiplexer, but then you can play with the data line and have C and C bar, like what is done over there. All right? Okay. Okay, let's do one more example. Come on. For some reason. Okay, just give me a second while we'll continue. All right, okay. So how do we solve that problem? Well, the trick over there is, what did I say? I said it was a something like, let me open Word over here. Yes. Oh, okay, yeah, set, nice. No, let me do it on Word. You know why? You'll get caught on the lecture capture then. But it was a good idea anyway. Okay, so we have sum. So it says function f of 4 variables, right? Function f of 4 variables, a, b, c, d is equal to, and then symbol, sum of, or not sum, it was a product. Yes, it was a product. It looks something like this, okay, but just know that it's not exactly that, right? Product of max terms, it's actually the gamma function. This symbol here is pi, but the one which we are actually using is the gamma function, right? I don't know if gamma is here somewhere or not. Gamma. I can't see any gamma. It will be there. It's just a matter of finding it. It looks something like this, but not exactly that. Something similar to that. That's some other. Okay, so what numbers did I say? I said 0, 2, 4, 8, 9, 11, 12. All right, now, the first thing we do is, that is, what can you tell me about the truth table? On the truth table, right? What can you tell me about this particular function as far as the truth table goes? What are those addresses referring to? Those addresses are referring to the locations of all the zeros. All right? So what we do is we draw. Okay, now the other question is, so there are 4 inputs. There are 4 inputs. Therefore, what do you need? You need 2 to the power of, you need 2 to the power of 2, right? 4 is equal to, 4 is equals to 2 to the power of 2. So therefore, what do we say? We say 4 select lines needed. So what type of multiplexer will we use, guys? What type of multiplexer will we use? We'll use 16 by 1 mux, right? We'll use a 16 by 1 mux, right? Now, if we use a 16 by 1 mux, then what will our thing look like? Well, basically, you will have your mux like this, right? Okay, you'll have your mux looking like that, right? We will have an output line. Okay, usually there is no arrow, but I'm just drawing an arrow just to let you know. Okay, and there will be an output line. There will be some select lines. Right? There will be some select lines. Okay, so your select lines, how many select lines will we have, guys? How many select lines will we have? Well, we will have 4. 1, right? 2, 3, 4. Okay, So that will be your 4 select lines. Then you will have how many input lines? How many data lines? 16, right? You will have 16 data lines. So I'm not going to draw all of them, right? You will have 16 data lines. So you will end up with, this will be your D0, okay, that will be your D0, right? And then all the way till D16. Obviously, I haven't labeled it properly because, you know, not D16, but D15 rather. That will be D15, okay? That will be your D15, and that will be D0. And then there will be many lines in the middle. There will be many lines in the middle. Now, so that's what your general block diagram looks like. Your F output is over here, F of A, B, C, D. Let me just put that there, okay? All right, that will be your output, F, or you can just say F. This will be your select lines. Now, what do we connect over here to D0 and all that? Well, what do these give you the addresses of? This here. That's the addresses of all the zeros. So obviously D0 will be 0. Which lines will have 0 connected? 0, line 2, data line 4, data line 8, data line 9, 11, and 12. Obviously, if those lines are the 0 lines, then what happens? What's connected to the other lines, the remaining lines? It's going to be 1s. So that's how you solve that. All right? That's how you solve that. Okay? So so that's how we apply a multiplexer. All right, guys? So that was that particular problem. Now, these are some of the particular chip numbers. Now that you have been doing labs, you're starting to get familiar with what chip number is related to which lab and so forth. Okay, now I now want to talk to you about another device known as a demultiplexer, right? It is the exact opposite. It is the exact opposite of multiplexer. In a multiplexer, let's talk about what we had done yesterday. You had many data lines, and then you had a single output line, right? Okay, so you were using your select lines. You were trying to control which of the data lines would get connected to the output. All right, now over here, let's look at the 4-1 first. I always like to look at the 1 by 4, right? So look at again the naming convention, 1 by 4, 1 times 4, right? Which means input side is 1, output side is 4, right? Okay. So what do we have? You have the data line, and based on, so it's exact opposite, based on whichever is the select line is chosen, that's the one which will be connected to the data line, right? It's the other way around, okay? So so you have an input, right? You have an input. Let's say you have a walkie-talkie, right? You have a walkie-talkie, and you've got a lot of security guards or somebody, right? A lot of people out on the field, right? And then you're just going to change the channel number, right? So you are the input. You are speaking, and you want, let's say, security guard number 3 to listen to what, and you only want to speak to security guard number 3, you know? So what are you going to do? You change the channel, or you punch in channel 3, then you get patched in to security guard number 3, right? Okay, so you are in control because the input then you ask security guard, can you give me an update? Then you go to security guard number 0, then you go to security guard number 2. So that's the other way around, right? Okay, so this is the thing. Exactly same process applies. You draw a truth table, right? You draw a truth table. So let's go ahead and have a look at the truth table. Oh, my camera is still down. Okay, so the main points, all right, over here is you've got the naming convention, 1 by 4, right, which means 1 input, 4 possible outputs. But not all 4 of them are connected at the same time. Only 1 of them are connected to the input. You've got the same select lines, just like how you had in the multiplexer. Now, the truth table. The truth table. What is output D0 equal to? Output D0 is equal to D when S1 and S0, when this is 0, 0, right? 0, 0. So you please draw a truth table in your exercise book, because I don't have access to the camera. Something's wrong with my camera over here, a document camera. So 0, 0, you have to draw S0, S1, right? 0, 0, 0, 0, this is most significant bit, all right? S1 is most significant bit, S0 is least significant bit in the select lines. 0, 0, obviously data line 0 gets selected. So whatever the data D was, right, gets connected to thing. So gets connected to, so your output D0 is equal to D, right? Now when you, and then when it's 0, 1, D1 is equal to D. 1, 0, D2 is equal to D. 1, 1, D3 is equal to D. Now, just like yesterday, from the truth table, we start to apply our concept of sum of products. So for each line, you develop a Boolean expression. For each line, you develop a Boolean expression. Now, what is the catch here, guys? What is the catch compared to yesterday? Compared to a multiplexer circuit, what is the key difference here? All right, okay. You're in the right direction. Have a look at the Boolean. I think you drew a circuit yesterday for the 4 by 1. Or was it part of your homework or something? For the 4 by 1, you drew a circuit. What did that circuit look like? Can you tell me what that circuit looked like? 2 level, right? Firstly, it was 2 level, right? And then how many outputs? Okay, 2 level. First level was AND gates. The second level was a single OR gate. And how many output? Single output coming out from that OR gate, right? Over here, can you tell me, will there be an OR gate? Huh? Will there be 2 levels? No, no 2 levels. It'll be 4 different circuits because it is multiple output circuit. 4 different circuits, right? But the inputs are tied in together. The same inputs getting jammed into, into all of those 4 circuits. So 4 AND gates, but the inputs are coming in together, all right? The inputs are fused, but the output is 4 separate output. Over there, in the other case, well, the inputs were similar as well, but the output merged again as 1 output, right? So I want you to draw that circuit. That's why it says, can you draw the logic circuit? Now, I'll show you the 1 by 2 case. Now that you've understood the 1 by 4, the 1 by 2 is easy, right? Now, when S is 0, select is 0, D0 gets connected to D. Therefore, D0 is equal to D. When select line is 1, D1 gets selected, right? D1 gets selected. So D1 gets connected to D, and D1 is equal to D, right? So if you put it in a truth table, right? The truth table will have only 2 columns. One is the S column, that's the input side. Output side is your D0 and D1, right? Then you then find that using the same concept, these are your Boolean expression. And have a look at this. Can you see there's 2 outputs over here? 2 outputs. Of course, you need a NOT gate and all that, right? Okay, so that's your logic diagram. Now, similarly, as part of your homework, I want you to develop the. I want you to draw, number 1, the block diagram. So write this homework down. And sometimes, guys, this is not primary school that I'm going to check your homework. You know, I'm expecting that you guys are keeping up, right? Okay. Now, number one, I want you to draw the block diagram of a 1/8 demultiplexer. Of a 1/8 demultiplexer, the block diagram. Block diagram looks like this. That's your block diagram, right? A chip diagram. Block diagram or chip diagram. Number two, draw the truth table. Now remember, this is the catch. In the truth table, for every output line, there is a separate column. Yeah? So therefore, in this one, how many output lines were there? How many in your truth table? There would have been 4 output lines, right? 2 input lines and 4 output lines. So it would look like this, guys. Let me show you. So for the 1/4, oh man. That's the name, Demux. Your truth table would look something like this, guys. S1, let's just select S0, D0, D1, D2, D3, because they are 4 separate lines. There are 4 separate output lines, so each needs its own. Yeah? Okay? And then obviously you then do 0, what? 0, 0, 0, 1, 1, 0, 1, 1. And then you populate the output side accordingly. Right? Obviously, when D0, when you have this, then you don't write a number, you write D, because data line D was getting connected. And obviously, all other cases, it stayed down. Yeah, that's how you do it. Okay, so then for each line, obviously, you have a formula. Right, so for a 1/16, I would like you, sorry, 1/8 I said, right? 1/8 Demux, I would like you to draw the block diagram. Secondly, I'd like you to draw the truth table, number 2. Number 3, derive the Boolean expression for each output. Number 4, draw the circuit of the 1/8 Demux using basic logic gates. Simple as that. All right? Okay? Okay. Now, let's look at the next topic, guys. So I think Demux, everyone is happy, right? I want to introduce you to another topic now. We've got another half an hour to go. I want to introduce you to another topic, which is also very interesting. But now that you've understood mux and demux, you will now look at decoders. By the way, guys, I just want to mention over here that I thank you for those of you. How many? Let's see how many guys here in class today. 1, 2, 3, 4, 5, 6, right? 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 38, 39 students, right? Okay. So I want to congratulate you. You guys are the lucky guys because you are attending lectures, you are in a better position. From here on, the course will change, the EE222 will change direction. It will become more difficult and more tricky. So as you've seen, like in the beginning, we were doing simple things like counting, binary addition, and all that sort of thing. Now, you're going to move into higher level stuff. In the past, you were using just basic logic gates. Now you are building higher level chips, like a decoder, a multiplexer, demultiplexer, adder, subtractor, using lower level gates, right? So now you would need to know. So you need to attend lectures, and please do encourage your friends to attend lectures. What I'm considering is maybe I might scrap test number 2, and I might split it into 3 quizzes, or something along those lines, right? Which is smaller, so that because in a test you could mess up big time, but in 3 separate or 4 separate quizzes, it's smaller exposure, right? Okay. Anyway, we'll discuss more about that later. Now let's talk about something called decoders. Now decoders. Let's look at this first decoder. I want you to note the naming convention. Once again, the naming convention is very important. How you write your n. You don't write capital A, small n, lowercase d. We write capital A and D to indicate that's an AND gate, right? Okay. Now, convention over here is 2 by 4, or 2 times 4, which means input side is 2, output side is 4. That's the first thing I want you to recognize. Look at that block diagram. Now, the point I want to drive here is, what does this device do? This is a new device called a decoder, right? And notice, what is the difference between a 2 by 4 decoder and a 1 by 4 multiplexer? Or 1 by 4 demultiplexer. What is missing between the two lines? Hey, here, document camera. Yeah, document camera. Yeah, so what is the difference between the two? So, look at this. It doesn't come on. And the other thing is, when we call from here, they can hear us. You can hear them, but they can't hear you. I was trying to talk, and they couldn't hear me, so I had to call from the mobile. Yeah, so just check that, yeah. All right, so there's no select lines. Obviously, there's no select lines. So this is a new device altogether. Do not confuse. They're not the same thing. They look similar, but they are totally different. All right, the way this works is that a decoder is basically, there is no external input line coming in, right, for the data. You want to turn on, this is a much simpler thing. So it was good that we looked at the multiplexer and demultiplexer to start off with, then we went into the decoder. The decoder is a device whereby you can control which line, one line at a time, to turn on and off. Okay? So in this particular case, you have 4 possible outputs. You have 4 possible outputs. And based on your selection over here, you can on one line and off the others. All right. Okay, so let's try this. 0, 0 on your select lines, right? Or this is like your control lines. We now call it the control lines. 0, 0 over here will turn on output 0 and turn off all the rest. Now let's think of an application, right? Okay, let's try 0, 1. 0, 1, right? That's the binary combination for line 1. Will turn on output 1 and turn off all the rest. So only one output is allowed to be on at one time. You can't have multiple. Only one output. So it's like you're controlling which one to go on, which one to go off. All right? Okay. 1, 1 will turn on output line 3. Right? And all the rest will be off. So please take note of that. All right. Now, let's consider an example. Where would this particular scenario be used? One possible example. Let's consider traffic lights. In a traffic light scenario, you have green, you have amber, you have red. There is no possible scenario where 2 lights, you can't have red and orange on at the same time. Yeah? Only one light can on at any instant. Okay? Only one light can turn on at any instant. So, how do you do it? You do it with this. Right? So what is the savings here? What is the driving factor? Why are we using some new device called decoder? We could have just simply had, 3 lines or 4 lines going to each of this, right? 0 line, output 0, output 1, output 2, output 3. And then just turn on one and turn off the others. Well, what we're doing in this particular scenario is we are saving on the number of lines. Using 2 lines, you are able to control 4 possible outputs, right? And similarly, you have 3 by 8. You want to try? Okay. Similarly, you have 3 by 8. Using 3 lines, you are able to control 8 possible data lines, 8 possible output lines. But remember, only one output to turn on at a time. So whatever the address you assign over here, A stands for address, right? Whatever address you assign here, that's the particular part which will go on. Now another part, well, this is heavily used in computer memory and all that, because you want to access a particular memory. So obviously you turn on, you get the address of that particular memory, so that particular memory turns on and feeds in. All right? So that's how we do it. Okay, now another concept which I wanted to show you. So that's 3 by 8. Obviously there would be 1 by 2, 2 by 4, which means 2 address lines, 4 possible outputs, 3 by 8, 4 by 16, and so forth. Now, let's look at the Boolean algebra. Let's look at the Boolean algebra. Now, for the Boolean algebra, before we do the Boolean algebra, we want to look at something called a, before we look at the Boolean algebra, we want to look at the truth table. Now, just before we start off with the truth table, I want to show you something over here. Have a look at this block diagram, right? 2 by 4 decoder. And have a look at this decoder. What can you tell me the difference between the two decoders? The bubble. Yes, the bubble. Right. What does the bubble mean? The bubble is the other way around. So obviously in the first instant, what was happening in the earlier diagram, guys? What was happening in the earlier diagram? When you assign, let's say, 1, 1, 1, 1, which output would go high? Output 3. And all the others would be low. So obviously if you put a bubble, what does the bubble represent? Bubble represents a NOT gate, right? It's a silent NOT gate. Not silent, but it's a short form of a NOT gate, right? So obviously, if we now apply, in this case here, a 1, 1, what would be the behavior of 0, 1, 2, 3? Right? All would be high. 0 will be high. 1 will be high. 2 will be high, because it was originally supposed to be low, but because of the bubble, it got flipped over, right? But 3 becomes a low, right? So that's another concept which you will face very common, especially if you're using circuit maker. You'll see when you load some of those chips in real life, the chips use low, logic low, right? Okay, so instead of making something high, it produces a logic low. So that's why you will see the bubble is always there. And I would like you, as homework, I want you to go and look up the data sheet of this guy, 74LS139. 74LS139, and also have a look at the data sheets of these guys over here. 74LS157, 74LS153, 74LS151, right? 74LS, right? 157. Okay, now let's have a look at the truth table. Let's do the truth table. Let me know, right? Okay, let's do the truth table over here. Okay, so we want to look at a 2 by 4 decoder. Okay, 2 by 4 decoder. All right, how are we going to do the truth table? There are 2 inputs. How many outputs? 4 outputs, once again. Okay, and what's our input numbers? A1, A0, address 1, address 0. Output is O, O0, O1, O2, O3. All right. Now, we are considering this one here, guys. The one without the bubble, all right? The one without the bubble. We want to do the truth table for that. So 0, 0, right? There is no connection to a data line. It simply is just 0, 0. We have O0 will go 1. The rest will be 0. Oh, sorry. O0 will go 1. The rest will be 0, right? Okay, in this particular, the one without the bubble, eh? Okay, 0, 1. Maybe if I put it like this, half and half. There we are. 0, 1. A 1 will be 1. and the rest will be 0. Right? Similarly, you can see the leading diagonal. There we are. That's how it's done. Right? Yeah, sure. Okay. All right. So now, for each of those lines, you've drawn the truth table, right? For each of those lines, I want you to write beside the truth table the Boolean expression of that output. What is that output equal to? In this case, there's no D. There's no data. There's no another variable. It's all ones and zeros now. So line number 1, it'll be O0 is equal to, right? Line number 1, you have O0 equal to, what? Can somebody tell me? A1 bar, A1 bar, A0, right? And A0, right? Okay. So O0 is equal to A1 bar and A0 bar? Yeah, okay, right. Okay, now what's the other one, guys? Let's go next one. Next one. The next one will be A1 bar followed by A0. O2 will equal to A1 bar, sorry, A1 and A0 bar, right? And the last one, output 3, O3 is equal to A1 and A0, right? So, yeah. Oh. Okay. Okay. Yeah, we'll just finish the lecture another 5 minutes to go. Right? Okay. So, guys, so you see, then from those Boolean expressions, I hope you've written them down. From those Boolean expressions, what do? You develop a circuit. You develop a circuit, right? So that's a decoder. There we go. It wasn't too hard. Now, obviously, if I give in your problem sheet, I say, hey, I want you to draw the Boolean expression for this, what's going to change in the truth table? Because of the bubble, what's going to happen? Everything will be flipped. On what side? On the output side, because the bubble is on the output side. But please be careful. Sometimes the bubble is on the input side as well. So you have to be careful. But it's not too hard. You just have to track it. Okay? All right. Now, there we go. This is, so for your homework, I want you, then obviously, after the Boolean expressions have been extracted, what do you want to do? You want to draw the 3x8 or the 2x4 decoder with basic logic gates, right? So let's have a look at the 3x8, 74LS138. That's the name of the chip, 74LS138. 3 address lines. That's why you use the word A, standing for address. In that case, it was data. There was a data being fed in. Over here, there's no data. It's just address, right? Okay. And then you have 8 outputs from O0 to O7. And you have to draw the truth table. Over here, the truth table wasn't drawn properly. So I want you to, for this particular thing, draw the truth table, right? And then once you've drawn the truth table, how many input, on the input side, how many lines, how many columns? 3 columns, right? And how many, for on the output side, how many columns? 8 columns, all right? Okay, and obviously there's going to be like a steady stream of zeros, not ones. Everything will be 1 except for there will be a string of zeros in a diagonal. Why zeros? Because of the bubble, all right? Then for each line you will extract the Boolean expression. So O0 is equal to, O1 is equal to. Now, eventually you will end up with a very large, you'll get 8 equations, but you will end up with very large circuits as well, right? You will end up with very large circuits. Okay, now, and as I was saying, one of the major, well, I started off with traffic lights, but the major application of decoder is in memory selection, right? That's how, so we're now moving towards how a real system works. Decoder, again, was built using what? Just basic logic gates, but it's sitting on one chip. So what they've done, when they developed the chip, they soldered, they got all the, they wrote all those chips into that particular thing, right? So using this decoder, this is the select line, and this is how particular parts of the memory get selected to output something. Okay, guys, there is another one. Before we finish decoder, there is now, before we finish off this today, there is another chip known as the encoder. But because you know decoder, encoder is the exact opposite. Exact opposite.